example here. So we have said that these are the values that we are going to have. So now let's solve it. Okay. So firstly, the question says that we are using that air standard analysis, called air standard analysis. So what is that? Let me add this light here. But we don't have. So we have to use the cold air standard analysis. What it means is that you can calculate the properties of the air at the environmental values. For this question, that so calculate, for example, like the CP, and you can take the CV value, or you can take the density, okay, etc. You can calculate it at environmental values. For this question, the environmental value is 98 kilopascals and 30 degrees Celsius. You can use these environmental values to calculate the properties of the air. And also in the thermodynamic analysis for the cold air standard analysis, this is the one. And the second one is that the air to fuel ratio. Okay, so instead of talking about air to fuel ratio, let's say that for the analysis we don't consider the fuel, we only consider only air. Okay, so if it is combusted products, okay, even the combusted products, they are treated as air. We are looking for the values of air instead of we don't consider fuel separately. Okay, that will be part of the combusted products, and it will be as air. Okay, now let's try to solve the problem one by one. And the first thing here is that so we can start from 2, 3, and the 1, 4. I should add that one to the expansion compression processes for all the thermodynamic cycles. Expansion and the compression processes. Okay. These expansion and the compression processes are isentropic. Okay. Isentropic means that the S2 is same as S1. Okay. When isentropic condition is satisfied, and the first is that it should be internally frictionless, or it is called also internally reversible. Reversible is more general term than the friction. Anyway, internally frictionless, and the second one is that it is adiabatic. Okay. Now with this in our mind, let's start. Okay, the question says find the horsepower of it, but we will try to find all of the values. And what I will do is that I will write the chart here. So you will have what you will need is you will have the 1, you have state 2, and the state 3 and the 4. This will be our chart for the problem. Okay. And what we are needing is that you need the pressure value, you can need the temperature value, or you can need the internal energy, you can need the entropy value, etc. So these values are the required values. Okay. And also you can need the specific volume. To find the values at any state, if you remember the Gibbs phase rule, the Gibbs phase rule says that it is that you need to know 2 properties, okay, 2 intensive properties. So for this case, all of them are intensive properties. The 2 intensive properties must be known. If you know 2 intensive properties, you can find any third. So for the question, we have the T1 and the temperature 1, which is the environment temperature. The process starts at 98 kilopascals and 30 degrees Celsius. Sorry, that is 4. The 4 is the environmental state, and the 1 is unknown. Okay, 4 is the environmental state, and the 1 is unknown. So therefore, so that I can write the 4 as the pressure value is okay for the 4, and temperature value is okay for 4. Because here you start the process. You have the compression, you have the ignition or the combustion and expansion, and then Q out, and then back to the initial point, which is the 4. Or you can renumber it, and you can put 1 here, 2 here, and the 3 and the 4 there. It doesn't matter, at the end these are just numbers. But the process starts from here, from 1, and with the initial values of the temperature. So I can just write the values here, which is given in the question. The value is that let me write the values here. So that P1 is 98 kilopascals, okay, and the temperature at 1 is that 30 degrees Celsius. 4, sorry, 4. And the next is that we are going from 4 to 1. Okay, and I've said that the expansion and the compression processes are isentropic. So if it is, so from 4 to 1, it is a compression process. It should be isentropic, and the S4, I can find it, and S4 will be the same as S1 because it is isentropic. And the fourth stage, since I know two properties, Gibbs phase rule, if I know two properties, U, S, N, and it can be found easily. So I will put some tick sign here. So these are found because Gibbs phase rule is okay. Now comes state 1. I go one by one. For the state 1, I know the entropy value, which is S1 is same as S4. This is the entropy value. And for one state, I know something else. No, I don't know anything. So therefore, for 1, it is only the entropy. And for the second stage, which is the state 2, also, this is the end of the combustion process. It is given as a T maximum, which is 1200 degrees Celsius. Okay. For state 2, I know the temperature, 1200 degrees Celsius. Okay. And for the state 3, so I don't know anything, but if I could find one more property for state 2, I could solve the state 3 too, but I don't know any property for state 3. But I can just write that S3 is same as S2, okay? Because that 2 and the 3 is expansion process and isentropic, therefore the entropy should be the same. And from that the 3 to 4, I know that the specific volumes should be the same. Okay. So that here specific volume 3 and the specific volume 4 is the same. You can see they are the same line. Similarly, 1 and 2 has the specific volume same. Therefore, that the new one same as new. Okay. So for the state 4, I can find the specific volume for the state 4. And if I find the specific volume for state 4, I can find the one more property for state 3. Okay. But for any other states, I don't have any given values here. Therefore, the problem cannot be solved. Okay. To solve the problem, I need some additional equation. I need some equation. I need some value that will help me to solve the problem. Okay. Firstly, let's start from the state 4, and let's find the unknown values for state 4, and then see what happens at our next stage. First, the internal energy. I will go to the chart for air. So you are always working with air. Table A17 or 18 should be. So for table A16, it is A17, and the temperature is that 30 degrees Celsius, and it is that 305 Kelvin. That's the temperature. And for that temperature, I'm looking for the internal energy, which is 217.67. Okay. But for the exact value, you need to interpolate it. So I can just tell the value of the interpolation if you are. So that internal energy at, let's see, do I have the value for the internal energy here? I don't have the value for the internal energy, but here, if you do the interpolation here for 305, you will get that 207, and it goes one by one. If you look at from 300 to 305, it goes one by one, It should be about 216.5 or 217 you can take. So for internal energy, 217. Okay, but you should work with, these are approximate values. Okay, you should work with the interpolation to get the exact value. Okay, now comes the specific volume value, and to find the specific volume value, it should be P nu, it is equal to RT. So P4 nu4 is equal to at R into T4. Okay, and from here I will find that the nu4 is equal to RT4 by the P4 value. Okay, and now replace the values. R4 air is 287 multiplied with the temperature at 4 is that 303 Kelvin, should be in Kelvin scale, and the P4 is that 98 kilopascal times 10 to the power of 3. Okay, this is the new value, and if you calculate the new value, you will get that the new one, you see, so that nu 4 is 887.9 per kilogram. Okay. That is the new value. Okay, let me write it here, 887.9. So I know the new value for state 4, and I can find new value for state 3 because they are the same. Okay, good. Now one more, but it doesn't help to solve the problem. To solve the problem, I need one more stuff, and this can be determined by this relationship. V minimum is the 0.1 times the maximum volume. That is given in the question. By using this relationship here, as well as by given the diameters and the lengths of the stroke, I can find the volume. With this one, I can find the volume, displaced volume. Okay, this one will help me to find the displaced volume. And from this displacement volume, I can find the minimum volume, and I can find the maximum volume values, and then I can find the mass from state 4, and then I can find the specific volume at any state. Okay, now let's try to find first the volume value and then other properties. So the displaced volume is, if you remember, that will be equal to, this one is the piston, and the piston has a circular and shape, and this one is the diameter of the piston, and this one moves from the top dead center to the bottom dead center. Okay. And the distance that it travels is stroke. Okay, so it moves from that one it moves from that center to this one. Okay, it moves up and down. So if I multiply the area of the piston, which is pi d squared by 4, and with the stroke length, L of the stroke, I can get the displaced volume, which is V max, minus the minimum volume. I can find it, no problem. So let's write the values here, that the displaced volume, the diameter is 90 millimeters, and the length is 100 millimeters. This one is 90 millimeters, length is 100 millimeters. Okay. The question says that also the maximum volume and the minimum volume 0.1 relationship, 10% of it. So therefore, instead of that one, I can write 0.1 multiplied with V max. Okay. And from here, you can calculate what is the value of the maximum volume. And for that value, let me see. V maximum is first the displaced volume, let me write it, and then the maximum volume. Maximum volume value is, displaced volume value is 0.306, and you have 362 meters. This is just calculation you can do by yourself and find the values. Maximum volume value is that 0.00 and 0.7069 meter cubes. Okay. Minimum volume value is, so it will be 10% of that one, and therefore you will add one more zero here, 1, 2, 3, and one more 0.69 meters cube. Okay, this is the values. These are the values. Okay, now let's do one more step here, that I know the new at stage 4, if I multiply this nu at stage 4, I can find the mass. Okay? And then if I find the mass, I know that these are the, let me show it here. This one is the minimum volume, minimum specific volume, and this one is the maximum specific volume. Okay? Because that nu is the volume by the mass. Since the mass is constant, this one is the closed cycle. Okay? Mass is constant, therefore the volume is only volume changes. So if it is maximum volume, that means that maximum specific volume. If it is minimum volume, it is minimum specific volume. Then if I can find the mass, then I can find new values for this stage here, and I can solve the problem. Now let's find the mass. And the nu at stage 4 is 887.9, and this nu value is the maximum nu. So to find the mass, I will work with the state 4. State 4. The mass is constant, M4 is same as the M, and that is constant. You should know it. And the specific volume, nu4, will be equal to that volume at stage 4 divided by the mass. And from here, nu is the max. That one will be that volume max divided by the mass. And the volume mass, I know it, which is 0.000709 meters cube. And the specific volume maximum amount is that 887.9 kilograms, meter cubes by kilogram. Okay. From here, the mass value becomes the mass of the system is, should be somewhere here. Mass is 7.961 times 10 to the negative 7 kilograms. Okay. This is the mass. Okay, so that since I know the value of the mass, so what I will do is that I can find the nu 1 will be equal to volume 1 divided by the mass, same mass. And I know that the volume 1 is the minimum volume, so that one will be minimum volume multiplied with divided by the mass. Okay, and therefore that you can find the nu 1, which is the, so it will be 80, write the values and then divide. Minimum will be that 0.000, that again 0.709 meters cube, and divide by the mass will be 7.6961 10 to the negative 7. This will be just the 10% of this one. It will be 88.79 meter cubes per kilogram. Okay, so I have found the nu at stage 1, which is 88.7. So it will be 88.79. I have found it, and nu 1 is same as nu 2. Okay, no problem. And the nu 3 is same as the nu 4. Therefore, so I have the values for stage 1. I have the values for, so it means that the state 4 is okay. I can find any property for state 4. And for state 1, since entropy at state 1 is same as entropy at state 4, okay, and since only the entropy value is required for this one, now I can solve the problem, find the unknown values for state 1. So let's do that. And S1 is same as S4. Therefore, I will use isentropic relations. Isentropic relations, okay, for ideal gas. And to find the isentropic relation for ideal gas, I will open that slide for you. Okay, so isentropic relations, ideal gas, and we said that we are using that cold air standard analysis. Therefore, we will use the constant specific heats here. Okay. And then you will use the isentropic relations. For that isentropic relation, you can find the temperature relations, or you can find the pressure relations, or the specific volume relations. Okay. I'll go back to my question here. Okay, if I go back to the question here, so for this question, at state 1, I know the specific volume. At state 4, I know the specific volume. Okay, and for state 1, I can find the pressure and the temperature by using isentropic relations. Now I will find the temperature firstly, and the T1 and the T4. T1 divided by the T4 will be equal to, let me go back to the formula here. So that T1 by T4, it will be equal to that nu2 by nu1, k to the power of 1. Copy these formulas. So T1 by T4, it will be equal to that nu4 by nu1 and to the power of k minus 1. Okay. This is the temperature values. Or you can work out the pressure values, and you can find that P1 by P4 will be equal to nu4 by nu1 and to the power of k. We're just using the formulas here, and T1, T4 relationships and mu pressure ratios. By using these relationships, you can find the temperature at state 1, and you can find the pressure at state 1. And the temperature at state 1 with that relationship will become, let me see, because here we have the state 4 is the, so therefore in this case it will be state 2, and the temperature is 444, will be 444.1 degrees Celsius. That's the temperature for state 1. Okay. And it rises to, it's not 1400s, actually it is 1200s. Correct values here. It's 1200s. It's at 90 millimeters. 100 millimeters. 80, okay. I should correct the values now. It's 400, okay. And the volume values, they are okay. And the let me correct the volume values here. So that pressure is okay. There's no problem with nu, and the mass value is okay. Displaced. Everything is okay. Good. Now the temperature at state 1 is 464.1 degrees Celsius. I have found the values for state 1. Now the values for state 2, it is okay. I have found both of the values because I know the temperature here and the specific volume relationship. I can find any third property. State 4 is okay, 1 is okay, 2 is okay. I know two properties, temperature and the specific volume, temperature and specific volume to state 2. And for state 3, I know only the specific volume here, but again, it is isentropic. For that isentropic relationship, so that S3 is same as S2, and again, using isentropic relations for ideal gas, I can use this relationship here, say that the T3 divided by the T2 will be equal to that nu2 divided by nu3, k to the power of negative minus 1, and then P2 divided by that P3 will be equal to that nu3 divided by nu2 to the power of k. So by using these relationships, you can find the temperature and the pressure values. And for the temperature value for state 1, for state 3, you will have that 405.4 degrees Celsius. Okay, so I know the temperatures, I know the pressures, I know the entropy values, and I know the specific volume values. Okay, so let's find the power of it. Okay, so to find the power of it, what you can do is that, so the power, you get the power from the 2 and the 3. Between this part, you have the work out, and from 1 to 4, you have the work input. Okay, first I should find the work output, and then I should find the work input, and net work output will give me the power. Okay, so let's solve it. So that work out, it will be between 1 and 4, between 2 and 3 actually. And to find the 2 and the 3 work, I will write the first law, and the first law says that delta U of the system, since it is closed system, and will be equal to that in minus out. Okay. For this problem, there is no out because it is adiabatic. This one is adiabatic and reversible isentropic. Adiabatic and plus reversible, internally reversible or frictionless. Therefore, there is no Q out here. Q out is 0. And there is no work out because it is compression process. For this one, you will have the work in, and Q in is also 0 because adiabatic. And delta U of the system, and it says that in the question, you can use the cold air standard analysis. If you use the cold air standard analysis, I've said it, you can calculate the properties at 98 kilopascals under 30 degrees Celsius, and you will take the constant values. Okay. There's that. You can take the constant values for the cold air standard analysis. See, the cold air standard analysis, you will use the Cp, Cv, rho, etc. at environmental values. Okay, and this one will be the constant. Because if you use the environmental values, it doesn't change, and therefore the values are the constant. Okay, now let's solve it. Instead of delta U, I will write M and the Cv and into, then process goes from 2 to 3, you will have the temperature at the 3 minus temperature at 2, you will have the work in. Okay. And the M value, we have found it 7. Degrees Celsius, and the temperature value at state 3, it is gives 405.4 degrees Celsius. So 2, 3 is expansion process. I should look for the compression process, which is 4 to 1. So I'm trying to find the work output. Okay, then it should be 3 minus 2, and here you have the work output, okay, not work input. This one is the expansion process. Therefore, here you have the work input at 0. So Q in as 0, Q out is 0, work out is not 0. Therefore, this one will be negative work out. Okay. And the temperature at state 2 will be, temperature at state 2 is 1200 degrees Celsius. Okay. Then from here you can find the work out. And the work out value will be that, let me see, 0.4541 kilojoules. Okay, you say that 451.1 joules. This is the work out. Now you can do the similar relationship for the work in, and the work in process happens between the states 4 and the 1. Let's do that for work in process. So that first law, again, I will use the work in, and it happens between process 4 and the 1. So that will be delta U of the system will be equal to, again, in minus out. Okay. The in process for this one, Q is 0, you only have the work in, out is 0, and delta U will be MCV, and you will have the T1 minus T4. T1 minus T4 will be equal to work in. M is same, CV is same, and the 1 temperature and the 4 temperature is that 464.1, which is 64.1 degrees Celsius, and the T4 is 405.4 degrees Celsius. And from here, you can find the work in value. It will be equal to work compression 0.248 1 kilojoules or 248.1 joules. Okay. This is the work in and this is the work out. But we are not interested in the work out amount, but we are interested in the work net out. Work net out will be that work out minus work in. And that one will be equal to the difference of these two values, 4.54.1 joules minus 248.1 joules. Okay. That one will be that work net out. Okay, it will be 0.206 joules. That is the work net out. Okay. So this is from one cycle. Okay, so that work net out, let me write it here, 206 joules per cycle. Okay. In one cycle, you get this amount of the work. Okay. Now let's go back to the question here. It says that where is that? You have the omega, which is 2000 RPMs. That is the rotational speed of the engine, so that omega is 2000 RPM. Okay, and but we should convert it into the seconds, so it should be that 2000 divided by the 60, and it will be revolutions per second. Okay. In 1 second, you have, let me see how many revolutions. If you write it in, so that in revolution you will have in 1 second, let me see, it is that 33 revolutions per second. In 1 second you have this amount of revolution, but in one cycle you have this amount of the joule. Okay, but since it is 4-stroke engine, let me go back to here. The question says that it is 4-stroke petrol engine. Okay, in 4-stroke petrol engine, in one cycle, okay, you have 4 strokes. But these 4 strokes happens in 2 revolutions. Okay, because that the piston is here, and it moves up. This is 180 degrees, it goes back 360 degrees. It makes 1 revolution, okay? And then the piston moves up again, it makes 180 degrees, and the back 180 degrees again, and it makes 2nd revolution. And for the first one, for example, you gotta have the combustion process, compression, and then you have the expansion, and then you have the intake. So exhaust, and you have the intake. You have 4 processes at 4 strokes, but these 4 strokes makes 2 revolutions. These make 2 revolutions, and therefore in 1 cycle you have the 2 revolutions. Now let me write it: 206 divided by the 1 cycle. This is 1 cycle, and in 1 cycle you have the 2 revolutions. Okay, and the piston rotates at 33.30 revolutions in 1 second. You can see in 1 second you have this amount of revolutions, but in 2 revolutions makes 1 cycle, and 1 cycle makes this amount of the joule, and this will be the power. Now let's cancel out the units here. Cycle cancels out, revolutions cancels out. You see at the end you have the joules by cycle, joules by second. And you can work out the units power value here. So I will wait for your comment. What's the final result? Let's see what do you have as a final result. What will be the power of the engine? You tell me if I can finish the lecture today. What will be the power of the engine? So let me add one more question here. This is for the 4 strokes. Okay. So the power of 2 strokes. So what will be the value of the power of 2 strokes? If it is 2-stroke engine, what should be the power? So the first, the value of this one, if you have the value, I will wait for your value and then finish today's lecture. Okay, let's see what's your value. What's the result? So this one is joules by second. It's also watt. Okay. Okay, of course. Okay, let's see. 3433 says Javid. Let's see that if it is true or I don't know it. But, or the 3.4 kilowatts, yes. 3.4 kilowatts. Let's see one more answer. Yes, Tapdıq Abdurrabbin. Yes, you are all right. 3.4. All of them say the same answer. Okay, now I will ask this question for you. But what if the strokes is not 4, but it's 2 strokes? What would happen if I have the 2-stroke engine? Will the power be more or it will be less? Let me give you 2 options. The power will be more or it will be less. The thing that the result will affect. Instead of having 4 strokes, I could have the 2 strokes. What will be the value for the power? Is it more or is it less? Okay. The same, but with more torque. Same, less because revolution. Yes, Nazim, you're right, but not less, more, or we will see that, but revolution plays a role here. So if it is 2-stroke, now let's see what will happen. We are assuming that we get the same power, okay? We get the same work. We are assuming this is the same. Okay? Assume same. Then you will have 206 joules per 1 cycle. Okay, and in 1 cycle, for the 2-stroke engines, how many revolutions do we have for 2-stroke engines? In 1 cycle, you have 1 revolution. Okay, because in 4-stroke engines, it moves up and then down. It moves up and down. You finish 1 cycle. But in 2-stroke engines, it moves up, goes back, and cycle finished. And this up and the down motion makes 2-stroke, but 1 revolution. 1 revolution. What I mean by revolution, that is, you have the connecting rod, you have the crankshaft here. You have the crankshaft here. And this one, I cannot show it in, I will not be able to show it in animation here, but if you imagine it, that the connecting rod moves up, the crankshaft moves 180 degrees. Okay, this one moves 180 degrees for crankshaft. And then the connecting rod comes back, piston comes back, the crankshaft moves the next 180 degrees. Therefore, in 1 cycle, you will have 1 revolution. And then the same, assume the same here. Same. And therefore, you will have the 2 times of that one, which makes 6866 watts. You can see the more power, 2-stroke engines, you can see more powerful than the 4-stroke engines. Okay, the torque of the rubber doesn't play any role here because the torque only plays a role when you talk about this compression ratio. Where is that? Compression ratio. Torque only plays in compression ratio. But if it is not compression ratio, then there is no any importance of talking about the torque. Let me show one animation here if there is. So animations for the 2-stroke engine. This one is first a 4-stroke engine. So let me start the animation. You can see that the piston moves down. Let me increase the speed here. So one revolution has been finished. The piston moves down, and second revolution. You can see one more time. First stroke, 180 degrees. Second stroke, 360 degrees. One more stroke, again 180 degrees. You can look at the crankshaft here. Okay, you should look at the crankshaft. The crankshaft makes 360 degrees. Okay, so this is for four-stroke engines. In the four-stroke, you finish the cycle. In four-stroke, you finish the cycle, but it makes two revolutions. Okay, for now, let me start one more time difference. So it moves now 180. You can see 360. Again, it comes to here 180 and then 160. And I think you can imagine now what's happening in four-stroke engines. So 4 strokes makes 2 revolutions. Now let me show the 2-stroke engine. What will happen if it is 2-stroke engines? 2-stroke internal combustion engine. If it is the 2-stroke engine, you can see now it starts to move. Increase the speed. It starts to move. You can see that in 2 strokes, 1 revolution finished. See, it comes down 180 degrees and moves up 360 degrees. In 2 strokes, you have the 1 revolution. Let me show the PV diagram. You can see PV diagram now. Okay. This is the main difference, the advantage of the 2-stroke engines. But the disadvantage, I have said, is it is scavenging. We call it as a scavenging process. In 2-stroke engines, you can see that intake and exhaust processes happens at the same time. You can see this one is intake. You can see the intake process opens. You can see, but exhaust is also open. You can see they are open at the same time. Decrease the speed. You can see it. Now the intake port will open. So the intake and the exhaust, they are happening at the, you can see this one is also, there is inlet and there is exhaust. They are happening at the same time. So therefore, the gas exchange processes here are very important. If this intake fresh air comes too early, then there will be mixed with combusted products, and then you will not have enough power. But for 4-stroke engines, that's not a problem, because for 4-stroke engines, you have a different cycle for intake, and you have different stroke for exhaust. Okay, good. So with this one, I finished the Otto cycles, and I stopped the recording.